Hi everyone, I'm Amik Malhotra, and today I will be presenting to you a possible way in which gravitational wave anisotropies could be used to probe the inflationary particle content. Now, since inflation is central to what I'll talk about today, let me begin with a lightning review of what inflation is. Now, inflation is a period of near exponential expansion in the very early universe that was originally postulated to solve the horizon and flatness problems of hot Big Bang cosmology. In its simplest incarnation, inflation is driven by a single scalar field whose energy density is dominated by its potential, and inflation takes place as long as this condition is met. Now, inflation also provides a mechanism to generate the seeds of the CMP fluctuations as well as the large scale structure that we see today. These are the scalar or density perturbations, but inflation also generates perturbations of a tensor nature, so gravitational waves, which would show up at interferometer scales as a stochastic gravitational wave background, or at CMB scales through the B-mode polarization of the CMB. Now, when it comes to gravitational waves, from this minimal scenario, these are expected to be completely Gaussian and unpolarized. They will also be red tilted, so they'll have increasing power on the larger scales. And most interestingly, their amplitude can be directly related to the energy scale of inflation, which would make a detection of these gravitational waves extremely valuable. Now, so far, the most stringent bounds on this tensor amplitude come from the non-detection of the B-mode polarization of the CMB, and in the future as well, next generation CMB experiments like LightBird, CMB-S4, and so on will further lower this bound or even possibly detect such gravitational waves. Now that's the story as far as the large scales go. What about the small scales? Now when it comes to the minimal scenario, the gravitational waves in that scenario are unlikely to be detected even with futuristic interferometers because they will be simply too weak to be detectable. On the other hand, if there is some sort of small scale enhancement of the primordial gravitational wave background, one might possibly detect such a background with the next generation of interferometers. Now, such an enhancement is indeed possible in several ways, the most common of which is the presence of additional fields during inflation, which could directly source these gravitational waves on these small scales. Now, in the presence of such a small scale signal, we would naturally conclude that the dynamics of inflation are not exactly those of single field slow roll, but something more rich. And in fact, we can try to learn more about these additional fields by looking at non-Gaussianity in the tensor sector, since non-Gaussianity can be considered to be a probe of the primordial interactions. In particular, if one looks at the squeeze limit of the bispectrum, which corresponds to the momentum configuration in which there is one extremely low momentum mode noted by KL, and the other two momentum modes are high momentum modes denoted by K1 and K2. Now, in the presence of such additional fields, let's say they have a mass M and spin S, the squeeze limit bispectrum coming from such an additional field acquires scale dependence coming from the spin and mass of this additional field, but also an angular dependence in the angle between the low and high momentum modes, with PS here denoting a Legendre polynomial of order S. This is in fact essentially the cosmological collider physics idea first proposed in these papers and also studied in many more recent papers. So can we detect such non-Gaussianity at interferometers? Well, unfortunately, not directly. The reason behind that is that gravitational wave backgrounds are a superposition of signals coming from different directions in the sky. And since these signals propagate in an inhomogeneous universe, they get phase shifted by random amounts, and which tends to completely Gaussianize and the signal and destroy any initial non-Gaussian correlations that might have been present. In fact, this result is much more general, and in fact, it was shown in this paper that any endpoint function consisting of an odd number of the strain variable h cannot be reconstructed due to these propagation effects. Now, how do we get around this? One possible way is that we looked at in a paper is to look at the ultra-squeeze bispectrum via the anisotropies of the gravitational wave energy density. This energy density is quadratic in the strain and hence insensitive to any of these decorrelation effects. The ultra-squeeze bispectrum here refers to a momentum configuration in which the low momentum mode is at CMB scales and the two high momentum modes are at interferometer scales. The idea behind this is that in the presence of such long and short mode correlations, the long mode induces large scale variations in the energy density at the short scales, and consequently anisotropies in the gravitational wave energy density. Taking the example where the long wavelength mode is a scalar and the short wavelength mode are two tensors, the anisotropy is roughly given by FNL times the primordial scalar amplitude, which comes out to be 10 to the minus 5 FNL. FNL here denoting the strength of the bispectrum relative to the power spectra, and roughly gives a measure of the strength of the primordial interactions. What's also interesting is that these anisotropies are correlated with the large scale CMB anisotropies since they are sourced by the same scalar perturbations. Now, continuing with the scalar example, let's say one has an additional spin-2 field during inflation that sources the gravitational waves and also contributes to this scalar tensor bispectrum through a diagram of the following form. Now, since this is a spin-2 field, this bispectrum requires a quadrupolar angular dependence in the angle between the low and high momentum mode. And this quadrupolar angular dependence can be seen when one cross-correlates these gravitational wave anisotropies with the CMB anisotropies, leading to a significantly different scaling of these anisotropies with the multiple number L, as compared to the case where there is no angular dependence. And thus, the presence of a spin-2 field can be inferred from looking at this cross-correlation. Now, we also looked at the precision with which we can measure this FNL parameter, so the strength of such anisotropies, and naturally, what we see is that for larger FNL and stronger monopole amplitudes, you can measure this FNL with greater precision, which is to be expected. What we can also see here is that the effective signal to noise ratio comes from the very first few multiples, and that is because gravitational wave detectors have limited angular resolution and are roughly limited to about an Lmax of about 15. Now let me also mention that it is possible to see the effect of the scale dependence as well if one looks at the scale or frequency dependence of these anisotropies. Now I remind you here that this scale dependence coming from this term nu, where nu is related to both the spin and the mass of the additional field. So in principle, it is possible to have measurements of both the spin and mass through these anisotropies. Now, all this plus analysis of specific models and the case of 3 tensors you can find in these 2 papers, which I refer to you for more details. I'll stop here for today. Thank you all for listening, and I hope to see you at the discussions.